Stuff. Okay, let's begin today's seminar. It is my great honor to introduce Leshem Choshen, who is a postdoctoral researcher at MIT IBM Joint Program. Leshem is excited about developing AI models that are open and collaborative. And really, the big picture here is that we want to build models together so that we can join forces and build models in a more efficient manner. He's excited about broadly pre-training and language model, effective AI model development research. And to do this, he has had a few notable contributions. He has been leading a few notable research projects on model merging. He's also been a co-organizer of BabyLM challenge, which focused on developing small and effective language models, which made a big buzz in the field. And I think that the topic of today is going to be natural extension of those ideas, as you can see, on recycling existing fine-tuned language models. I would also note that Leshem was chosen for a postdoctoral Rothschild and Fulbright fellowship. With that, let's welcome Leshem.
Okay, thank you for the introduction. Let's head to it. So I assume it won't be big news that not many of us can pre-train. You can raise your hand if you pre-trained any model in at all. Okay. Okay, it's like, I think it's could be 10 million and more data, then it counts. And on the opposite, how many of you fine-tuned or adapted the model, maybe parameter efficient fine-tuning, full fine-tuning, those kind of things. You don't see maybe the hands, but there was this one hand for the first and all of the hands later. And basically this talk is going to ask or to lead us towards the big goal of could we take those two facts, social facts, let's say, and make them into pre-training together. Could we get a lot of small fine-tuning and small adaptations into pre-training? And one thing before I go ahead, feel free to ask questions. I have more content than we would reach in the slides, and I prefer just focusing on what interests you instead of another paper. I'll have less papers and more interest, better for me and hopefully for you. Okay, so for today, I would not focus on zero shot and things like that because those do not change the weights. They're useful, but apart from this talk. So the main paradigm is you pre-train a model and then you fine-tune it for some reason. Then the most obvious question would be, instead of doing that, could we choose a single model, go to Hugging Face, take one model? Could that be a better model than the pre-training model? And we have papers on that, but I would also not focus on that unless you ask questions, and then happy to discuss it more. Basically, there are cases that you might be better off by taking one of the fine-tuned models and not just a pre-trained. Probably the most common case that you can think about today is instruction and chat models, which is basically fine-tuning a model. But today, I'll mostly focus on the third paradigm, asking what happens if instead of taking one model, let's say from Hugging Face, could we take two models, three models, and get one model that is better than any of them for the purpose of general fine-tuning. So I don't care about the abilities of this specific model. I don't care if I use anything at all from those three models. I only want that this would be useful for new tasks for my new tasks that I care about. And something interesting that I'll present now and we'll reach it to the end. There's a last step that you can do, and that is repeat it. If you had, let's say, 3 models, and we combine them into one model, which is better, then now we can fine tune on that because it's better. Then we can get another 4 models. Those would be better merged together again. Okay, so that's a better model. Why not someone else come and say, I'll start from this? And then someone would come and say, I'll fix the biases in this model. So here is a new fine-tuned model. And someone else says, yeah, but it's not good on machine translation. So I added something for that. And I fine-tune and I slowly adapt my model in a collaborative manner. So that would be the last thing we're going to discuss. But first things first, why do we even pre-train? So a lot of different approaches to what pre-training gives us, but for like the framing of this talk, think about pre-training as just a machine learning artifact. If in a normal state of things, when you train from scratch, you randomly choose a seed. You choose weights and you say, okay, I'm doing gradient descent from some point. This is my random point. Pre-training basically gives you another point. This is a point in a very vast space, which is a better initialization than a random initialization. A fine-tuned model is another point. Maybe it's better than that. Maybe I can play with the numbers and get another point which is better. Of course, when I fine-tune, I get another point. If I could have started from that, that would obviously be even a better initialization. So let's think about pre-training as like a point in a very weird multi-dimensional, let's say 1 billion dimensional space. Okay, a lot of introduction. Let's talk about merging. The idea is we have a few fine-tuned models and we want to get one model out of them of the same architecture that generalizes better. The first thing we need to know is that the normal thing or the normal state of this kind of approach would look at ensembling. In ensembling, we would have the same input, 2 networks, and then the network is just a parametric function, right? It's just something I put the input into and get outputs. I average the 2 outputs, right? Here it would be the 2 AND rows. I get the same input twice and I average the outputs. In merging, I average the parameters of a very nonlinear function, right? A neural network. And I hope that this magic is going to somehow make sense. So it's not proven that this would be an average. It's not even proven that when I average 2 weights of networks, it would give me any reasonable function. And indeed, for our purpose, maybe it even doesn't have any meaning. Maybe it's just a good place to start from, right? Because if what we need is just an initial seed, maybe that's even just that. So the most obvious thing we can do is averaging weight with doing nothing smarter than that to get 2 models together. And let's see with experiments whether it works. So we took, what's that, like 8 or 9 tasks. We fine-tuned, and now we have multiple models. We're asking what would be the results if I use a pre-trained model and evaluated on a lot of models, or on one of those fine-tuned models and evaluated on a lot of models, or on merging 2 of those models. So you'll have a table, and in the table, every cell is a merging of 2 models and whether it went well or not. So now the magic comes. big table that is hard to read, but is green and yellow, right? That's the first impression I would get from it. So what are those numbers mean? On the diagonal, you see what happens if we just took one of those models. We didn't merge anything, we just took a model trained on SST and evaluated it on a lot of other things. The number in every cell indicates how better that point is when compared to just using the Pretrain model. So for example, using COLA, the topmost model, is worse than using the Pretrain model, and using SST2 is better. Now, every color tells us whether using the merging of two models is better than taking the single model as a starting point. Yellow means it's better if I take randomly, it's better to take the merging. Green means that the merging is better than the sum of its parts. That's usually a complicated figure, so I'll give you a second to tell me what you don't understand. So I have heard, so I'll repeat and tell me if it's not what you've asked. You're asking whether any of those results are based upon having the same domain, because otherwise it won't work. Yes. So in the same domain as vision and language, yes, because it's the same. I assume it's also the same architecture. So we don't have a lot of architectures that do everything at once. But inside the language domain, we try to get as different tasks as we can, because we wanted something that would showcase that it works better. When you have, for example, just different seeds of the same task, it also works, but maybe it's not as surprising and not as interesting. So it works also for very similar cases, but this is trying to get a diverse example.
When combining these, when training on these tasks, do we train only on the input that's given in the data set, or we also added prefix or some sort of instructions that in plain language describes what the task is about?
So it depends on, so in this very specific table, it's just fine-tuning with nothing else. But it sounds like in other experiments and other papers also with the prompts and things like that. And when you have prompts, generalization is usually better. It's easier to merge those things, which I think is also intuitive to some extent. No, so here everything, yeah, I think everything in this presentation, to be consistent, I think I left zero shot out of all of the figures. It's always fine-tuning over a lot of tasks and averaging. So the question is that a good fine-tuning place to start from? It's often when you have something that is capable of doing zero shot, so this is D5 and it's like not great, it's a specific figure, but like in general, it works for zero shot things as well, but you cannot do iteration. Like, why do you have multiple fine-tuned models to merge if you're only doing zero shot? So you need a case where zero shot makes sense. Okay, so I think like we'll sum this figure. In general, it seems that taking two models is better than the one. It's maybe is or maybe not better than the Pretrain model. But if you have two models, just merge them instead of taking one of them. So the next obvious question is, okay, but what's special in two? Could this thing scale somehow? So we took the best single model from here and merged it with others. So now the diagonal would be pairs of the best model with COLA, best with the SST, and so on. And the table would be all the triples. And you can see that now it's not as green and yellow as before. So basically what this coloring tells us is that when you merge 3 models, it's not better than 2 models anymore. There's also the numbers here you might see or you might not see. Suddenly all of the numbers are positive. So what we get when we average more models is that it's not better anymore than less models, but it's very consistently better than the pre-trained model. So it seems that you get some kind of averaging effect. So when you get a lot of things, at some point you get new knowledge and it's consistent, but you can think about it as a bias variance trade-off. The variance goes down and there's some interference maybe. You cannot get more and more results by aggregating more and more models, at least not by averaging. But we would want to have more models. So one thought is that the thing we're lacking here is interference. When we have 2 models and they learn different things and we average them, then we might keep some of the things that each one learned, but we also divide by the number of models. So when we have more models, every signal from every model that was learned is going down. Like we're not using the signal as well as we could. So in the next paper, in ties, we focused on 2 such interference cases. So let's assume we have 2 models, and this is a single weight and how we act upon it. So we have a single weight, we average it, and we get somewhere between what the 2 models, let's say, voted. One said it should be high, and one said it should be middle high, and we get some average. Nice, okay, makes sense. Now, what happens when one model says we should increase this model, this size of the weight, and the other says, no, we should decrease it? At that place, we get just something small, right? You get a small arrow to some direction, and in some essence, there is no single model that ever wanted to update in that manner. So it's not that we got a fine-tuning of what exactly should be the weight of the size of this weight. We just got something that is close to 0 because they did not agree. And if we can think, it's a bit of a stretch, but if we think of one weight as having some knowledge, then one model wanted one knowledge, another model wanted something else, and we said, okay, so nothing. So that's the first kind of interference. And the second kind of interference that one can think of is whether maybe one model said this should be updated a lot, and the other models just didn't really care in some intuitive manner. So if the updates are really small, do they really mean that this should be not change? Or do they mean the gradient descent didn't find anything there, so it doesn't matter to this model whether you increase this weight or not? So could it be that when each different model learns something, it updates it in certain weights, and all of the unchanged weights are just there and anything can happen there? And to get some to know between those 2 cases, let's take another step and take a step back from merging multiple models and look at a single LoRa model. Supposedly, LoRa is parameter efficient, right? It uses the parameters well. But we know that all of our context of learning is based on over-parameterization, right? We can create any function, or like we can approximate any function with the weights we have. So when we have a very large model, it's large to be over-parameterizing the pre-training. But in the LoRa step, we are reducing the number of parameters because the training data is small, and we can still do that. It still would learn something, it would still be over-parameterized despite reducing the number of parameters that we change. And the question we ask is whether we really use all of those parameters, or is it still in a very over-parameterized regime where even LoRa, which is only, let's say, 1%, I think, of the general weights, is it using the weights sufficiently? So we did a very brute cut into the LoRa space. You can see the purple line. We took some tasks, trained LoRa's on them, and then started deleting weights just by magnitude. So we delete the smallest weights, the 10%, 20%, and so on, until we got to about 90% of the weights. And you can see that deleting weights almost doesn't matter. So even when LoRa has all of those weights, in some essence, it doesn't care about the weights it learned. It cares about 10% of the weights that the LoRa trained on. So efficient, but not really, like the outcome is still not efficient in that sense. And then we took another step. You might be familiar with norm growth. I'll say no. So norm growth is like a common phenomenon that we see that when we train models on more compute or more data, the norm grows or keep on growing. So if you have another epoch on exactly the same data, you would see that the model is more or less in the same direction, but the weights become bigger and bigger with training. And if we follow, if we take this into consideration, then it makes us wonder, wait, maybe the magnitude also doesn't matter that much, because we know that if we'll train more, we'll just get different numbers. So now the second thing we did is like only the 10% that we didn't delete, we made them binary. The other plus or minus, right? We talked about signs before. We're asking whether LoRa even cares about the actual magnitude of things. So now we took LoRa and we have 10% of the weight of the LoRa, and there are binary 10% of LoRa, and we have one norm just to get the LoRa in, because obviously it needs some weight. So it's like minus alpha plus alpha. And you can see that doing that did not decrease. You would expect it not to decrease by much over LoRa. But in fact, what we found is that this even increases the performance of a LoRa. That would be the bottom table. And it increases the performance of LoRa's more as the model we're starting with is bigger. So if we go back to the over-parameterization hypothesis we have the same amount of data, but we keep on using bigger models, and the LoRa is taking a percentage of the model, not a percentage that takes into account the amount of data we're training on. So we can expect to have more noise as we train LoRa on bigger models. And this is what we think we see. We see that the advantage of throwing what we think is noise, or what empirically is not helpful, is a better thing to do as you work with bigger and bigger models. Yep.
I wanted to ask maybe two questions. The first is, like if you observed any sort of difference across different like difficulties of the fine-tuning task. And then the second is basically how does the like the lower dimension D change things if at all up a little?
Yeah, so the first question, it would have a simple answer that we didn't try, and I think it's one of the things that did bother me. What controls, so the size of the model controls the size of the LoRa we're training. Okay, nice. But the real question is, how many parameters do we really need? And in that essence, I would assume that, yeah, for more data, it's obvious that you need more because you just memorize or something more. But I agree that there's an interesting question of whether every data is just as informative. And it's a question that the only thing I can think of that try to address it is, to some extent, the physics of, I don't remember how they call it, but like the physics of language models or something like that, where they try on pre-training to assess different characteristics of the data and see whether, like they try to show that every parameter in some essence gives you 4 bits of memorization or something like that, and try to play with that. So if those directions interest you, I would look a bit there. About the rankings, yeah, I think we have the graphs of different ranks and how it affects them. And I think it's more or less what you'd expect. Okay, so we understood that LoRa is very not efficient, if you want to call it that. And now we can go back to merging and say, okay, so if a lot of those updates are noise, and it makes sense because gradient descent has to learn something. Gradient descent has a probability of 0, if you want, to give you any update that is, like, to give you 0 and not something is something that gradient descent doesn't do. So it makes sense that you would have things learned that were not the thing we needed, but just some trials during the training. If that is the case, then we can assume that those should not even be taken into account when we merge models. When we see the update that the fine-tuning did, we can ignore the part that the model did not change, because the model really cares on a very specific part of what it learned. So now let's get back to all of this, a bit more intuitions and get an algorithm together. So in order to merge models, we take, let's say here, 3 models. We first cut all of the weights that are irrelevant. Everything that is small, we just say, okay, this is not really a part of the update. Now we make a majority voting over directions. So if all of the models made the same direction, nice, but if there's disagreement, we just look what directions more models want. And true, the fact that some models want something else means that this kind of idea would probably suffer, but it's better to have something that at least helps most of the models than to have something that is not useful for anything. And then the last thing to note is that when we select all of those, now when we merge, we only average the weights that we kept. So instead of dividing by the number of models, we divide by the number of weights that exist and were not deleted. So those would be like dividing by 1, 1, 2. So I divide by less, and then I degrade the signal less. Right? If one model learned something very unique, it would be the only thing kept, and we would keep it. You would be very surprised to hear that this works well. Specifically, I think interesting is that you can see that now when we have more and more models or models trained on more tasks, the degradation over how the degradation of the benefits from new models degrade more slowly. So we can merge more models and still see benefits of it. Still, we see a clear decline. It's not that we can take the 1,000 models of Hugging Face and expect anything, basically. But we can take, let's say, 5 instead of 2. So we solve some of the interference. It also got general results, and ties is like one of the main methods people use now for merging. So practically this looks well, but that's, you can use, if you want to use it, less interesting. Okay, let's skip it a bit. Just one thing you might have complained, and you haven't, is that all of those, like until now, I all the time talked about a weight as if it bears any meaning. But maybe the first thing we learn in linear algebra is that a weight doesn't mean anything without a basis. So in a different basis, this weight might be 1,000 weights. So why do we even assume that all of those models share an interesting basis between them? Yeah, maybe because of pre-training and all kinds of those things, but surely with LoRa's, they do not have shared basis, because if you know LoRa bit, there's some random initialization there. So basically, we show that you can find the basis, you can put them all with a bit of tweak over SVD, but you can take a lot of models, find the basis, and this would get you better generalization than just doing the same things with weights. So now when the weights have meaning, you can take any other merging method and it would help you. I think that's good enough for now. Questions?
I don't think I understood the B matrix, or do you mind?
Yeah. So
Say a little bit more about that.
yeah, let's see. Like, yeah, we don't. Okay, so in general, when we train a LoRa, we don't know if like it's known to everyone. You add another part to the matrix that should, like, you take, let's say you have a specific matrix that you want to add a LoRa to. You have A and B, 2 matrices that replace it. I know you know it. And the interesting thing in LoRa is that those 2 matrices are not of the same rank as the original one, but they have like the same input and output, but a very, you can think about it as like this kind of shape of a small rank in between them. Now, when you have pre-training, every time you fine tune, you start from the known W, the known metrics that someone worked really hard to initialize for you. When you have a LoRa, then you initialize one of those things as a 0, and the other you add random noise, basically, right? You start from some initialization. And because of that, each one of the LoRa's starts from a different basis you can think about, or might end up in a different basis, because they add to the same thing, but they are not aligned in a really good way. And also, like this was the thing I skipped, you can also see that in all kinds of CKA and things like that, they are not aligned as well as fine-tuning. We update it, so I think this is TKA, but we had some variations over this graph. I should fix the caption here. So you can see in general that the correlations of all kinds of things are much better when we look at two fine-tuning weights than in two loras. And this is something that you need to fix. Okay. So one thing that you should ask yourself is, why do any of this magic work? Like, we know that the high dimensional functions and their parameters should not, the reason that this is not a linear function is that you cannot average the parameters and get the average of the output. So what am I getting there at all? And there are some meta-learning sort of guarantees that are related to it, and there are all kinds of thoughts. But I'll try to give one direction that I feel gives some intuition over what happens in this parameter space. So I would try to talk about the space. We started with a single model being a point in a space. So we'll focus a bit more about it now. Each model that we talked about, the fine-tuned model, the Pretrain model, each one of those has a billion parameters. You can think about a billion parameters as being a point in a billion parameter space. And you can even have a billion and one and think that you have every point can be evaluated and get a loss over something, right? So that would give you the loss landscape. Different points in space are models, and each one of those models could be used to what you know as models, right? So this is like an uncommon way of thinking about models, and mainly because we're not used to think about more than 3 dimensions. And I don't know, maybe if you're a physicist, then 11, but not a billion. Still, one thing we're trying to show is that this still gives us interesting intuitions. And the intuition I'm going to try to tell you is intuitively this. If the pre-trend is 1 point somewhere in the space, when you fine-tune on different things, so let's say language tasks, apparently you don't end up somewhere in a sphere around the pre-trained model. You go in a certain direction. So even just the different training, they already have something in common that they all learn, something that very, very broadly, but that they agree on and improve the model in some missing aspect. But this is really a broad part of the space. Inside this space, you can find regions. You can find that if you trained several models on the same tasks, so let's say 3 models on different NLI, MNLI, SNLI, WNLI, something like that, you would find that those would still be close to each other in the space of the 1 billion parameters, despite them learning on different data, but similar data. So we find that the areas have some meaning attached to it. It's not that every model is just finding a very specific point, but the points, the whole region has some meaning or capabilities in every region. And you would not be surprised to know that inside the task region, there is a dataset region, where if you train on something very similar, like part of the same data, you end up finding models that are very similar in terms of their weights. If this is true, all of this just means something about the models we find. It would be especially interesting, and that's the other part I'll show is that points in this space, which means models that probably you cannot get from a gradient descent, but somehow relate to the models we found, those are also showing the capabilities of models that define this space. So if you just take a model, a point in the general region, it would be better in general language tasks than just any point. If you get a model in the task region, it would be better than a model in the general region for this task. And obviously, if you find something of the data set, it's better than something else. Okay, so a lot of intuition, and let's try to prove a little bit of it. I'll keep some of it to the paper if you want to read more, but at least some. So the first and easiest thing to show is what happens if we have a lot of models trained on parts of the same data set, and we just think about those as clustering. This is a T&E just for visualization, but what is more interesting is that you can see that each point here has supposedly two colors. The outer color is the clustering color, and the inside color is the gold label color. If the two agree, then it looks for you as just 1 point, and this should make the 3 points that are mislabeled pop out to you as, wait, the clustering did it wrong. So just again, let's think of the significance of what we're doing here. We're taking clustering based on cosine similarity. Why not Euclidean distance? If you remember norm growth, the size doesn't really matter, so only the angles in some essence matter. So we do a clustering over models, over weights, and it can tell us what data set we trained on. So if you give me you train a new model on, or a model of this architecture on a part of MNLI or all of MNLI or just a different seed, you can give me the weights and the clustering, basic, no fancy clustering, could tell you that this model was trained on MNLI. But I promised more, right? I promised something about tasks, which is less obvious. So the next step is we take, instead of 20 or so data sets, we take 3 different groups of tasks. We fine tune on different data sets of the same task. So topic classification, 1, 2, 3, 4 models, NLI, 1, 2, 3, 4, 5, and so on. And again, we just give it to clustering as is. And now you'll see, so the T&E is not as pretty as before, but the clustering, you can see that it has an error here and here. And all of the rest, it classifies well to groups of models without ever getting any information about those data sets. So it could tell you that you trained on some kind of an NLI data set just by the weights and by nothing else, basically. Questions before I go forward? That's might be an unintuitive point. Okay. In that case, I showed you half of what I promised. I've showed you that models are found in a specific region. But I wanted to know whether a specific region also applies to a specific capability. So if we take just models, again, just points, because now we have characteristic of this region by the model. So you can take any point in there. Would that act well? Would that be able to perform on the tasks in general? So to do that, as before, we have 3 different levels. We have general models, task region, and dataset region. And we're trying to evaluate each one of the points on a general part of this. So for example, when we pick a model from the from a task region, we evaluate it on multiple data sets of this task. Because we don't care about a specific one, we care about something that is captured in all of those tasks. I think simple and most intuitive way for people to visualize it, at least, is to take 2 models and look at how it behaves between them, right? So how do we pick models? We go between 2 models, and every point in between them is another model, and we just evaluate it again and again and again. We take a model from the general region and evaluate it on a lot of general tasks, and see whether the in between those 2 models, we get more general or less general models. And again, if you know nothing, you might have just assumed that each of those points is a basin, a very short place where you found something good, and in between is just random space. Why would they ever have anything in common with each other? And this is basically what we get. Again, 3 graphs for the 3 domains, but let's look at the big one. You see that, first of all, every point is better than the worst point. And the worst point is a point that was trained to do one of the tasks. So here, ESNLI, for example, is performing to some extent over NLI datasets, but it's worse than something that we got, which is just somewhere in space, not an outcome of SGD or anything like that we took. And then the 0.9 is more general than that. When we go to all of the line, another thing you can note is that the bottom is none of the 2 sides. So it's not that we can reach, it's not only smooth between the 2 models. The best point or the best generalization is somewhere in the region. So somewhere that SGD didn't get, and somewhere in between is a more general point than the sides. And this gives us already, so it's not necessarily half. So for example, just merging would not give us that. But still you would see that there's a lot of this bottom. And what merging basically is doing is just finding just any place in this region, because most of the places in the region seem to be better. So you can do a smarter optimization in some way. Not that we know the way currently, but supposedly you could, and get even better results. So why would merging work? Because all of this region is okay and generalizing and better. So, okay, let's just pick somewhere. We don't know how, so something is better than nothing. That might be known to you as linear mode connectivity. If not, don't worry about it. And in some essence, I'm saying that even that is not that surprising, because what we did now is find a line. But we go further and say, what if we didn't take a line and we just took points in this region? We just went and looked not for exactly the line between 2, but just points between a group of models. And I don't have the graphs because the visualization is very unintuitive. I have it in a spare slide if someone wants it later. But the idea is that you find that almost every model that you uniformly sample from this convex hull is better generalizing than the edges. And the edges is real models that we trained. So in that sense, we're saying that it's very easy to find a line that is good between two models because there's a huge multidimensional space that all of it is good. And because there's such a big space, which is all smooth and has nice losses between all of it for general purposes, you can expect to be able to do more and more optimization in this space. Questions before I show one approach to such optimization in a collaborative manner.
Clarification, this is not based on Kai's paper, right? This is
right. This is, in some essence, it's not based. Like you can think about it as a step back on just analyzing. Right, and you can think about it as normal merging because averaging is merging, so it's very easy. Yeah, but this just comes to show how Euclidean this 1 billion dimensional, supposedly no reason to be Euclidean space is. Okay, so one approach that I've hinted a lot about on how could we even look when we care about generalization and how could we keep on optimizing. Oh, sorry, I have another side note, a whole paper in one slide. Another side note is that all of what I talked about is how we combine things to get more generalization. But one thing you need to remember is that you can also combine things and forget, right? We talked about interference and assume that this is a bad thing, but it seems that part of the reason that all of those models work well and that the merging works is that it also forgets the things that different models do not agree upon. So when, for example, you take two biases, this is what we did in this paper, you train a model on the same task, but add a different bias to each model, then when you merge them, then each bias is going down because that's not shared and the interference somehow ruins this. But the performance on the tasks keeps is stable. So if you take this perspective, then when you merge different things, you keep what is shared, but you also delete what is not shared. And in some, like maybe your case or maybe a new thing I'm not thinking about, but the deletion could also be an interesting part and not only what most of this field is looking on is like how we combine. So when we combine, we also throw things and sometimes the throwing is interesting, for example, in biases. Okay. The last thing we can discuss is how do we do it again and again? And why do we want to do it again and again? Because if we know that when we merge a few models, we just reach some point, then we can expect that if we start from this point and train more, then we would not delete part of the things that were useful for both, but we would optimize to a better point that is close to it and gains new advantages. So the way we're doing it is basically thinking of a distributed way of training where everyone comes with their own tasks and they contribute their models to a central place. That place just merges all of the models and say, okay, here I got 8 new models. Here is a new model. You can use that one next time. Here is a new model. People come, they train. When they share 8 models, it says, I got new 8 models. I merged them. Here is a new one. And you keep on doing it ideally forever, but because we were doing it all ourselves and no contributor really helped us. So for a few iterations on 30-something datasets. how doing it looks like. So now we have a trajectory. It's not anymore one model. And you can see that with the iteration, so every iteration is merging multiple models. With iterations, first thing you can see is that it really trains. This, for me, looks like a very natural training curve of general stuff. But here, instead of having a batch, every batch is merging multiple full models that had a lot of gradients, unlike a normal batch that it's like one gradient over a lot of examples. Some things to note, red would be just fusing once. So you can see that as a comparison, you can see that there's a lot to gain even after merging. But also you might think about multitask learning. I would expect that this is the first thing that pops into one's mind. So yeah, multitask learning requires you to have all of the data and make all kinds of choices. So there are things you can do without. But the surprising thing is that apparently multitask learning is so hard to get right that for some reason our distributed thing improved over the multitask learning, which we thought is going to be a ceiling effect. And it was even improving over what was there, the state of the art of multitask learning, that obviously had more hyperparameters and like it had more data than us, and they did smart things. We just invented the new method and hoped it would work well. Here there were people talking about few shot and things like that. So here we also get that and see that few shot also improves in a similar way. And I don't remember, like general tasks also improve. I think that is, after all of the introduction, that should be a very easy slide. But it's all very positive. And if you're coming from a skeptic perspective, you'd say, what's not working here? What is the empty half of the glass? What could be not right in this? How could this even win multitask learning? You're cheating somehow. So multitask learning, it has some intricacies, and also we have more compute. So multitask learning is more efficient. But let's see something. So one thing you can think is that it won't generalize. And an interesting thing we found is that look at the top parts. So blue and yellow would be tasks that are part of the multitask task that we trained on versus just new tasks. And the surprising finding that we had is that it almost doesn't overfit. It almost gets nothing from it almost knows everything out of domain and in domain the same. And the reason for that is that if you remember, what we care about is a model that you can fine tune on well. So there is no real out of domain, in the sense that both of the in domain and out of domain see your data. The only question is whether this is a good starting point. I think that was a confusing point. I'll rephrase it. We created a model where this would be a good point where we can fine tune on our task and check result. So apparently, if this point was also the outcome of my data, I didn't gain much from seeing my data in reaching this point, because I'm always training on my data and getting somewhere. Most of the benefits, apparently, is from seeing other data to initialize my model better. In some essence, if you add to pre-training your data, or you just take a pre-trained model and then fine-tune on your data, you apparently can expect more or less similar results. You don't need your data to appear twice, both in pre-training and in fine-tuning. One thing is that we've seen averages. Maybe it doesn't help every task as well. So yeah, it doesn't, but at least it seemed to improve at least most of the tasks, and it doesn't hurt too many tasks. So good, although not perfect. We checked how much it would scale. So we had the scale we had 36 data sets, but we also tried to do it on one task and add more and more data and see whether we can integrate more data. And we didn't reach the point where more data didn't help, or that more contributors don't help. So we can think about it as like more people coming at once. Would that really break it? So it would make it a bit less efficient, but it still works. And yeah, as I said, there is a efficiency trade-off. So what this costs us is that every contributor needs the full fine-tuning, and when you merge it back, it's not as good as just training on. When you merge 8 models, you get something in the interference, and you could have trained on 8 models with less compute and get more or less similar results. So the overall thing costs you more if you're the one person doing everything. Yeah, so that's still in writing, but we also did it in an asynchronous way. So instead of taking each time 8 people, merging them, we said everyone can come whenever they want. We added the rolling average to account for it. Doesn't really matter. And one thing we keep on seeing is that it's, for some reason, it's still very good in not forgetting. So whenever you add something into it, you trained on a new task. Let's say you removed some bias and now you trained on a lot of other tasks. It stays fine. So you don't need to re-add your data all the time. And I think for continual learning people, that's and interesting, and for me it was surprising. Yeah, I think I had a lot of content. So happy to take questions if you still have any.
Okay. Leshem.
Slides with specific data. Like, what do you think are the difference between, I guess, like the tasks that did get improvement and tasks that did not? Because I guess, like, if you want like a lot of different people to contribute this, and if you only for some tasks, like, would you, like, for example, tell them like, oh, if your task is like have like this or that characteristic, maybe don't try this, like, that's what I'm thinking. So I was wondering if you have like any intuition about like why some tasks benefit and others.
Yeah, so some of the tasks, so the ones that had negative results, it was still small, but those are tasks that at least when you walk a lot with them, we weren't surprised to find those. They're a bit more noisy and they just move around a lot. So maybe it's even that, with some different seed, it suddenly would help. But there are definitely those that it didn't matter much to. So it's like maybe added something, maybe went down a bit. And I agree that if it would be very hurtful, people would not probably use it. But because it was mainly good or nothing, then I think it's safe to just say, okay, so why do you care? Just share your model, like be a nice person and do it. I think there still, if you really want to create the framework, one thing that changed is that I think less people are fine-tuning, and it's still something people do, but a bit less. And the other thing is that when you when you add all of those models, the benefit is a bit to the community, and you don't benefit anything right now from giving, which so it's a bit of an incentive of why would anyone bother. So that's still something that one day we need to solve, so people to care. Maybe because it's very popular, then they say we got, then we are giving back. But if we have something stronger, it would be good.
Thanks for a great talk. And actually, I was wondering if the model merging process is invertible, that is, that you merge several different prediction models, and then probably you adapt it into a branching path. And I was thinking if you can trace back to see which model contributes most to the final kind of predictions.
So the short answer is, well, it's obviously not invertible, but also I don't even know of a way that someone tried to separate what is giving what. Of course, unless you keep it, and then you have it. But that's but it's also related to a question I was asked like some time ago about interpretability. So I think it has some, like, maybe if you can focus on that, so you can delete a lot of the weights, and then you have a small part of the weight that even is doing anything, and then could you split this to some subtasks? So I think the same, it would be interesting to be able to do something like that. I don't know if someone trying, so maybe it's really hard. Maybe there's a very clean trick to do it.
We focused a lot on fine-tuning on a specific task. It seems like fine-tuning is the less costly part of our development infrastructure. Is mostly about pre-training. I wonder if you have any thoughts on like how this would tie back to the costly part of our development stack.
Yeah. So in the very broad manner, I think most of my research somehow tries to answer how could we make pre-training more efficient or faster or more accessible, something like that. So I think this is a certain approach that says if we have something very that many people use, then maybe someone could make the first effort and other people can start building on it. So you'd have a whole paper saying, I removed all of profanity from Roberta 0.3, or I don't know, Gemma 0.3, and now it's Gemma 3.1, and someone else would come and improve, and then you'll improve in steps. But you still need something that just trained on, I got syntax. There are other thoughts on, okay, could we improve architectures without pre-training? So the next one, pre-training, would be able, so there are scaling laws is one approach, just training small models and checking and only replicating when, like, once you did a lot of that, is another approach. BabyLM is one such approach we're doing, but it's not the only such thing we're doing. Also scaling laws. So there are a lot of other initiatives for other parts of it. And maybe even modularity to some extent might be the way, where you train a lot of different parts, or you have one model and you slowly grow it. And then you say, okay, this is a model that already exists. I don't need to reinvent it. But for the next model, I just have a way to grow it up and now train, and the training is easier and maybe can be done with that kind of thing because you build on something. So it's a bigger model, so all of this is new, let's say, and I need to train it. This maybe is enough to train in those kind of ways.
Thank you. And so let's take, oh, there's one more hand.
So I was wondering, you show results of different tasks, but does this work for really complex tasks like text image generation or 3D?
So I definitely know people using it in image and in text. So it's both. I'm trying to think if I know specifically on text and image generation. So like, for example, yeah, so there are things, like there are people using it on the fusion models, just I'm just a bit less familiar. I know I don't remember the results because they usually more of the methods. The people in Georgia Tech, I think, worked with VITs, so more of classification of images and things like that. Yeah, it's like I can surely say it's used in the image domain. I'm not sure in whether in image generation specifically, and I have the feeling that yeah, it was also in reinforcement learning. I'm quite sure it was used in diffusion model somewhere, but I'm trying to like pick a paper and say here they did it, and I can't think of one now, but there's probably somewhere.
Let's thank the speaker.
I have a question if there's time for another question.
The talk is over, but we will continue the conversation here. Go ahead.
Oh, I just wanted to ask, so maybe you already mentioned this, but in the part where you were talking about interpolating between two like models that were optimized for two tasks and then showing that, or rather two data sets, and then showing that like all models along that line are still good. Do you know whether if you trained a model with like mixed data training on both of those task data sets, whether that trained model would end up somewhere on that line of interpolation, or do you think it would be basically somewhere else in that space? Like, do you know if an answer to this exists, I guess?
Yeah, the speaker is really bad. Did you understand it? Like I half understand. So you're talking about the like the mode connectivity stuff. And you're saying something about what happens if we train and would it fall in that space, but I didn't understand what is this, like try saying it more, just maybe you will figure what the speaker is saying.
Sorry. I meant that so you talked about how just interpolating between two models that were optimized for two different data sets would still give you like some point in the middle of those two things would give you maybe the best performance. So I'm talking about the like ESNLI slide and the MNLI slide in particular. So I'm wondering if you had a model that was fine-tuned on both, like simultaneously, would that trained model, would that point be that same optimum, or do you think it would be basically somewhere else in that task space? Like, do you have any idea, I guess?
Yeah, so we tried all kinds of those variations, and by default, it doesn't lie in the like space between the two.
Okay.
So we tried like maybe using something like doing multitask in this space between the two and seeing how well does that work, but so far we didn't find something like that.
Okay, thank you so much.
Yeah, sure.
I have a question for you. You mentioned it's LoRa's on the to fine-tune the model, and I have an idea about how to create the industry model. I want to use industry data to fine-tune a new model to solve some industry problem. So, what do you think is fine-tuning way?
So you want to train?
Yeah, because some ChatGPT is a conversation data, and in the interaction science term. So I want to think about how do we create the industry model, for example, meaning industry or everything, because for the meaning industry environment, we can save the weather data or some machine data, others. The data type is different. So what do we do? For example, LoRa. I don't know. LoRa is a. I don't think LoRa is a good way for this environment. Do you think? I want to hear that your idea.
Yeah, so you just like, let's say you talk about something like tables or something like that, like something that is in the industry and not somewhere else.
Yeah.
And then you're asking, so like I think, whether you're using LoRa or full fine-tuning or anything else, it's among, so gradient descent methods are the best we have so far.
Yes.
It's like, it's not optimal, but this is mostly what we have.
Yeah.
And then between LoRa and fine-tuning, it's a bit of how much data you have, how much compute. There are some notes that claim that training that like LoRa is